Hello, welcome back. So today we'll start a new topic, sorting algorithms. Okay, so the plan is we'll use 3 lectures to basically cover I would say 2 kinds of very specific sorting algorithms, quicksort and heap sort. Okay, and we're gonna talk about quicksort for today. And there's a third kind of a bigger type of sorting algorithms, which is the constant time sorting algorithms. It is more a special type because well, it is linear time sorting algorithms because it has constraints on the input elements or the input types. So after we have covered all the sorting algorithms, we will use one more lecture to do the review before everything for the midterm exam. Okay, so our plan is that the first midterm will be on October 1st, Thursday. All right. Okay, so we'll get started with quicksort. Okay, and because we just finished the chapter for divide and conquer algorithms, and this quicksort algorithm is a very good kind of review of a divide and conquer approach. Okay, so its worst case running time is big theta of so for what chapters we'll be going to cover in midterm, I will talk about that in the review. But basically, the sorting algorithms will not be the heap sorts, and the linear running time sort will not be covered. Okay, so I'm gonna talk about that more specifically in the review section. Okay. So speaking of the efficiency for quicksorts, on average case, its running time is big theta of n times logarithm of n. Okay, and this is similar to the merge sort algorithm, right? We already know that merge sorts uses the divide and conquer approach, and quicksorts has the same running time efficiency as merge sorts. And it has another advantage, which is the sorting in place. So it doesn't, compared with merge sorts, quicksort doesn't require extra memory space. So remember, in merge sorts, we need to allocate 2 chunks of memories, the area L, right, the area R, to store everything in the left half and the left half and the right half within the input sequence. But for quicksort, we don't need that. It is an in-place operation, basically. Okay, so now let's look at how this quicksort algorithm is designed. It's also basically a divide and conquer, uses a divide and conquer approach. Okay, so given this input array to be sorted, okay, the array's name is A, capital A, and we have a starting index P and an ending index R. Okay, so the goal is to sort everything between index P and the index R within the array A. So the first step is to divide, and this divide is kind of a more sophisticated dividing step as compared to merge sorts. So we need to call some procedure named partition. Okay, later we'll see that procedure. So we will need to partition the array into 2 sub-arrays. Okay, with some index Q in the middle. Okay, and this partition needs to satisfy that all the elements to the left of index q, which is from p to q minus 1, should all be smaller than the elements aq. And all the elements to the right of q, from q plus 1 to r, should be greater than aq. Okay? So it is not just a simple dividing like what we did for merge sort. It is basically some rearrange. We need to place all the elements around so that the left is the smaller half or lower half, and the right part is a higher half with higher values. Okay, so of course this gonna cost us some computation time, right? We cannot do this for free. We need to do a bunch of comparisons, right? Basically, we need to go over all the elements so that they are rearranged into the proper half. Okay, and compared with the merge sort, to compare with merge sorts, the dividing step of the merge sort is simply to compute the midpoint, right? Which is the basically p plus r divided by 2 and rounded to the floor. That is the dividing step for merge sorts. Okay, so this is the first difference we see here. Okay, and the key operation in this partition step is to find the index q. Okay, so what elements we need to use as the pivot, as the elements in the middle that does the division. This is the key operation. Okay, and then the second step is to conquer. That is to sort the two sub-arrays, the first half from p to q minus 1, and the second half from q plus 1 to r, by recursively call the quicksort algorithm. Okay, so this is where the recursive call happens. It is a divide and conquer approach. So basically we need to use some recursive calls because we have smaller subproblems that are basically the smaller instance of the original problem. Okay, and the good thing with quicksort is that in the combine step, no work is needed to combine the sub-arrays. Okay, because they are already sorted. So the entire, after the conquer step is returned, the entire array is now sorted. Okay, so this is the, again, we can see the difference from compared with merge sorts. The merge sorts comes with the big theta of n running times cost for combining step, right? In merge sort needs to call the merge procedure that takes linear time to take all the elements in the sub-arrays and combine them into the final results, right? So yeah, that is a divide and conquer design flow of this algorithm. So we're gonna look at the final implementation first. Okay, it's quite neat. Actually, it's just 4 lines of code. Okay, the procedure takes the input array A and 2 indices P and R as inputs. Okay, so if you want to sort an entire array, just call quicksort on the start index, say 1, and the end index, the length of the array. Okay, so we're gonna see that it is just one 3 lines of code under the if condition. Okay, so if there's more than one elements in the array, then we need to do the partition, right? We call the partition procedure, which will return the index of the pivot elements, and then we will need to use the index of that pivot to call the quicksort recursively on the left half from P to Q minus 1 and call quicksort on the right half from Q plus 1 to R. Okay, that these 3 lines codes is only executed for input elements that are larger, that has more than 2 elements. Okay, so if there's only 1 element, then this one is already sorted. There's no need to call the recursive call, right? So yeah, very typical recursive algorithms, and it's also straightforward to realize that we can use master theorem to analyze the running time of this quicksort algorithm. But first of all, there's some technicality we need to deal with, which is the implementation of this partition procedure. Right? We got to somehow implement it, and we need efficient implementation. Okay, so next we're gonna look at the partition procedure. Okay, so this is the procedure we're gonna use, right? With inputs A, P, R, same input arguments, same input parameters as the quicksort. Okay, so the first line of code is to take the last element. Okay, we take the last elements at index R to name it X. So this X is the pivot elements we're gonna use in the partition, in all the partition steps. Okay, and then we initiate I to be P minus 1, which is 1 to the left of the starting index P. Okay, so right now it is pointing to some places outside the input array, because the input array starts from P and to R. So the initial position of I is P minus 1. It is 1 to the left of the input array. And then there's one from line 3 to line 6. It's just a for loop that iterates from P to R minus 1. So R minus 1 is 1 to the left of the ending elements. Okay, so we're not going to go iterate towards that ending index, because the ending index is already picked up as the pivot. Okay, so this is good news for us, right? Looking at this segment of code, we can see that there is just one short for loop. Okay, so a for loop without any nested structures, like there's no 2-layer for loops, is basically a linear running time structure, right? This for loop basically goes through all elements from left to right and use some if statement to compare each element with the pivot elements, okay? And if that element is lower than the pivots, then we will increment the I by 1 and exchange the AI elements with the current elements in the iteration AJ. Okay, so basically we are switching all the elements that are smaller than the pivot to the front of the input array. Okay, and there's a bunch of exchanges to be done in the for loop, and eventually after the for loop ended, we're gonna exchange the pivot, which is AR, also to the middle. Okay, and then the index of the new position for the pivot will also be returned. Okay, so because after AI plus 1 is switched with AR, then the pivot avenue is at the position of I plus 1, and that index will be returned. Okay, because according to the previous quicksorts, we got to use the index Q, which indicates where the pivot element is. Okay, so that's why in the partition procedure, we need to return the I plus 1. Okay, so we will use a simple example to show how this partition procedure works on an input array. For example, we have an input array that have 8 elements. Okay, this is the initial position of all the loop counters and the input parameters. So P and J, they are at the same position 1, because I is initialized to P minus 1, so it's 1 to the left of P, and R is the ending index. Okay. So in the first iteration of the for loop, we are comparing the 2 with the pivots 4, right? And the 2 is smaller than the pivot, so the if condition is satisfied. So that's why we will increment I by 1. So now I reaches 1, right? It moves 1 to the right, 1 position to the right, okay? And then we will exchange AI with AJ, because in the first iteration of the for loop, I and J, they are both 1. So this exchange actually does nothing. So 2 will remain in its position, okay? And then into the second iteration of the for loop, J incremented to 2, okay? So this time, J will be compared with the pivots, but we found that the if condition is not satisfied because 8 is larger than 4. So we will do nothing. The 8 will not be, so the I will not be incremented, and there will be no switch happening here, okay? So we will increase J by 1 more step to the right. Now, in the third iteration, J is 7, which is still greater than 4, so we'll do nothing. And then we keep increment J into the next iteration. Okay, so this time we hit 1, okay? So this time AJ, which is 1, is smaller than 4, so we need to increment I by 1 into this position, and then we exchange I with J. So basically, we will exchange the 1 with 8. Right? They will exchange position. So after the iteration 4, we will find that the 1 is moved to the moved to the head of the array, and 8 is moved into the middle of it. Okay, so J keeps increment into next iteration. 3 is also smaller than 4, so we need to increment I and switch AI and AJ. Okay, 3 is moved here, and 7 is moved into the middle, and J increments. Okay, let's keep on the iterations. Okay, 5 is greater than 4, so nothing happens, and eventually 6 also is larger than 4. Okay, so now we are going to the end with because after J hits I minus 1, we are done with the for loop. The scope, the range of the for loop iteration is from P to R minus 1. Okay, and then the line 7 will be executed, which is to switch the pivots with the current elements in I plus 1. Okay, so now we've got the final outputs, which is well, the outputs, the finally returned value is the index of the new position of the pivot, which is also 4. Okay, and but the array doesn't need to be returned because it is all in place arrangement, in place operations. All the elements in the input array, the input array has been alternated, has been altered. Okay, so nothing, no other elements need to be returned. Just the index will be returned. Okay. So now, if we look at the array, we find that the pivot is in the middle, and everything to the left of it is elements 2, 1, 3, and they are smaller than the pivot 4. And everything on the right, it's 7, 5, 6, 8, and they are greater than 4. Okay, this is what we need. That's all we need before carry out the next recursive calls of the quicksort. Okay, so the lefts and the rights, they are not. One thing we may want to keep in mind is that they are not sorted. They are not sorted. Okay, so they are also in basically random order, because we are not doing the element-wise comparison. We just split the So I see a question, how do we deal with the I initially again? So the I initially is P minus 1, okay? So it's okay if we have an index out of the arrays range, as long as we don't actually access that memory, right? For example, if the input index P, the starting index P is 1, okay, then the initial value for I is 1 minus 1, which is 0. Okay, that is okay because we are not accessing the elements A0. So nothing in the code, no line of code access AI other than this line. Okay, but before we access AI, we already incremented it by +1, right? So no matter what the initial value, even if the initial value is P minus 1, when we access it, we already increment the index. Yes. Okay, so that is how the array looks like when we call the partition on it. Okay. So this step, the choice of the inputs, the choice of the pivot elements is quite actually random or arbitrary, because we simply choose the last elements as the pivots. So we'll see in later slides that this step may there's some randomness in the last elements, because we don't know what it is. We just pick it as a pivot. So ideally, we want the split to be even. Okay, we don't want the first half to be very short and the remaining to be very long. We basically want to do an even split, and we'll see that there could be some technique can be used to achieve that to achieve that goal of attaining to more or less evenly distributed segments. Okay, so that's partition done, and let's analyze the procedure a little bit. Okay, so as I said, we select the last elements as a pivot. Okay, and basically we colored the regions into like the light shadow area, the dark shadow area, and the white area, right? So we are actually using this pivot to partition the array into 4 regions if we also count the pivot its own as a region. Okay, so everything here in the light shadowed area are the elements that are smaller than the pivot. Okay, as we are within the for loop iterations. So everything to the left of I, okay, it is smaller. They are smaller than the pivots, and everything between indices, index I and index J, they are those greater than the pivots, the elements that are greater than the pivot. Okay, and everything to the right of J is those that we haven't iterated over yet, right? Because J is the counter of the for loop. Okay, so at the start of the iteration of the for loop for any index, okay, if the k is between p and I, then the element should be smaller than x. Okay, so this is actually the so-called loop variants, the statements here. Okay, so for any index q, for any index k, if we can use these three statements as a loop invariants. Okay, so loop invariant is something that we have mentioned when we analyze insertion sorts and merge, also merge sorts. Well, not really merge sorts, but it is a technique that we can formally use to prove the correctness of the algorithm. So this is the loop invariant is an optional requirement, optional contents of this course. But I think it'll be interesting to use it to analyze the correctness of the quicksort algorithm too. Okay. So let's put the loop invariant here. So let's look at what the situations is like before we start the for loop. Okay, so before the first iteration, we can look at the value of I, which is p minus 1, right? And j is p. So the first two conditions is just previously satisfied because there's no elements between p and I, and not between ji plus 1 or and j minus 1. Okay. So initially it looks like this. There's nothing between I and j. Okay. And the maintenance condition says that in the middle of the for loop, whether if this loop invariant applies before the iteration, we want to see whether it will remain valid or remain true after the iteration. Okay, so that depends on how the if test turns out, right? Because within each iteration of the for loop, there is a if condition, and if that the outcome of the if testment, the if condition will determine how the iteration ends, how the array looks like, right? So we can consider the first case is that the current element is greater than the pivot. Okay, then nothing will be changed other than the incrementation of the loop counter j. Okay, and after the loop counter j is changed, right? For example, in this case, if the aj here is greater than the pivot x, so we will just move this little black bar to the right of it, and no switch will happen. Okay, so after the iteration moves on, everything in the dark shadow area is still greater than x, which means the condition 2 is satisfied. Okay, because we just naturally move it to the right because we have obtained an element that's greater than the pivot. Okay, and let's analyze the other case. Okay, so if the aj is smaller than the pivots, then we basically need to do what? We need to increment I by 1, right? And switch the aj and ai. So the elements that is smaller than the pivots is moved ahead to the position over there, right? At the beginning of the array, and this one, the elements that's already in the dark shadowed area is just moved to the end of the dark shadow area. Okay, so nothing in here will be changed. Okay, but there's one more new element moved to the front. Okay, so the inputs, so the condition 2 also remains satisfied. So that is the how the loop invariant is maintained after each iteration of the for loop. Okay, so the termination condition is that after the termination, we simply moves the pivots into the correct place. Okay, and so that's everything to the left is smaller into the pivots x in the middle, and everything to the right is greater than the elements in the middle. Okay, so with this more, I would say, abstract analysis of the iteration, we can better understand how the partition procedure works. Okay, so that's loop invariance. And again, this part is an optional it's not a required, but an optional content, which provides a more formal analysis into the correctness of the partition procedure. Okay, so what we care most about is the running time, right? But as we know that this is just one for loop is used, so it is actually a linear running time algorithm because we simply go through each element in the input array, and there's no nested for loops or other while loops stuff. So it's quite straightforward to see that this is a big theta of n running time algorithm. Okay. All right. So now it's time to think about the running time of quicksort procedure. Let's go back to the algorithm itself. Okay. So it's kind of tricky. We cannot use the traditional recurrences like how we did for the merge sorts, because for merge sorts we know that the midpoint is somewhere close to the midpoints is lower is n/2 to the ground, which is the left side, which is the size of the left sub array, right? That's for merge sorts. And to the right, it's the right half is n/2 to the cell, right? So for merge sorts, we can basically say that the T of n is 2 times T of n/2 if we tolerate the sloppiness of the flooring ceiling. Okay, but for quicksort, we really don't know the results of the partitioning. We're just choosing some random number, which is the end elements, the elements at the tail of the input array, and we partition the array into 2 halves. But we really don't know whether it's evenly partitioned or it is unbalanced partitioning. Okay, so we need to basically analyze the two cases independently. Okay, so if we're lucky that for each partitioning step, we all obtain a very balanced partition result, that the returned Q is almost in the middle of the array for all the partitioning steps, then it's easy to imagine that this quicksort basically runs as fast as merge sort, because all the sub-problems, they are almost of n/2 sizes of the original problem, almost half the size of the original problem. Okay, and if unbalanced partitioning is obtained, then that is bad news for us, because if we always have unbalanced results, then the algorithm can run as slow as in certain sorts. Although this is not likely to happen, but we definitely need to consider this possibility. Okay, and let's see why this is the case. Okay, so in a worst case partitioning, okay, we know that the results of the partitioning is the Q in the middle. The index Q is returned. So to the left of Q is Q minus 1. To the right of it is Q plus 1. Okay. So the first recursive call of quicksort on the left results in a a sub-problem of length n1. And when n1 is q minus p, okay? And the length of the second sub-problem is r minus q, and we denote it as n2. Okay, so we have n1 and n2. That's the sizes of the sub-problem. So we also have the idea that n1 plus n2 is the total length minus 1, because we're not including the pivot elements. Okay, so let's just consider the most extreme cases. Okay, so when the worst case partitioning occurs, the two resulted sub-arrays, one of them has n minus 1 elements, and the other has 0 elements. So that is the most extremely unbalanced partitioning result, right? So, and let's just do the extreme analysis. Let's just assume that extremely unbalanced partitioning happens in each recursive call. Each time when partition procedure is called, the result is always the most extreme unbalanced partitioning results. So in that case, because the partition costs big theta of n time, and let's assume that for the input sequence of 0 length is obviously it's constant time. It costs us constant time. So we can basically write the recurrence of the worst case partitioning. We can write the recurrence of the quicksort in such a form: T of n equals T of n minus 1 plus theta of n. Okay, so we need to keep in mind that this is the worst case, because we assume that within each partitioning step, the most unbalanced result is achieved. Okay, so we've got this recurrence. Now we want to solve it. All right. So this form, we can ask ourselves whether it can be solved by a master theorem. Well, apparently not, right? Because the master theorem requires that the form must be T of n equals a times n over b plus something, right? But apparently we don't have such a form. So this is not a case that can be handled by master theorem. Okay? So we got to use some tricks to get an estimate of the running time. Okay? And that is also a quite straightforward. Basically, it's some substitution like thinking. So we can further split the T of n minus 1 into T of, so we do the first split, right? We do the first substitute, we substitute this T of n minus 1 into T of n minus 2 plus big theta of n minus 1, right? And then we can further split this one into T of n minus 3, right? Plus big theta of n minus 2, right? And then we further split this one, right? So we will get something like T of 1 plus big theta of 2, big theta of 3, until we got big theta of n. Right? That's quite similar to the arithmetic series that we are familiar with. Right? Considering we are adding 1 plus 2 plus 3 to n, then the results can be described by a quadratic function, big theta of n squared. Okay, so we can attempt to guess the solution for the worst case quicksort running time. Okay, we can guess this could be a quadratic running time algorithm. So when we have a guess, we can use basically substitution method to kind of prove that our guess is correct. Okay, so using substitution method, we basically use mathematical induction. So we assume that this is true, this quadratic upper bound is true for a smaller case of, for the input case of a smaller size, say t minus 1. Say we have this inequality as our assumption, t of n minus 1 is smaller than c times n plus n minus 1 square, and c is the constant that we want to determine. Okay, so we use substitution method. Of course, here we let big theta of n to be d of n. So this d of n is something that we should know ahead of time, right? The question, say, if we've got question that tells us big theta is d of n, then this d is something constant that we can use. For example, it could be a concrete value, say 4, say 5, 6, okay? So we can think of d as something that we know, okay? So we substitute t of n minus 1 into this, okay? And then we will need to, we want the next inequality here to be valid too, right? We want it to also hold, we want this upper bound to hold for this larger case of inputs sequence. So we basically need to solve this inequality, right? So we can eliminate the quadratic term, right? See, if we expand this term first. So eventually we can solve C, right? We find that the C must satisfy this condition. It must be greater than d plus 1 over 2. And it must choose the n0 to be d plus 1 over 2 to the floor, to the cell. Then this inequality will hold. Okay. So anyway, this quantity, this upper bound, quadratic upper bound, holds from a smaller case to a bigger case. And that is the first step of the mathematical induction. Okay. So, and it's promising because the boundary conditions it's quite easy to find. Yeah, I can do that again. So this is basically following the okay, so let me write the formulas here if you have so we can spend this term here into c times n squared minus 2 times c times n plus c plus d of n, okay? And this one should be smaller than c times n squared, right? So we can eliminate c times n squared on the two sides. Hope I am correct. Okay. So let me move all the c's to the right. So to the left of the inequality, it's d times n, and it should be less than or equal to 2n plus 1 times c. That's correct. So c should be greater than or equal to d times n over 2n plus 1. Okay. So now we just need to make sure that the C is greater than this quantity, right? So let's see what we can do now. Plus 1. So this quantity has a upper bound. The function of n over 2n plus 1 has upper bound because when n approaches infinity, this quantity will approaches 1 over 2, right? And not sure how this one is approached. And 0 equals. Oh, it should be 2n minus 1. Okay, so this one should be 2n minus 1. Yes. So here it should be 2n minus 1. Okay, and also 2n minus 1. Okay. So this quantity should always be smaller than 1 over 2. No, greater than 1 over 2. Okay. And if n 0 is d plus 1 over 2. So maybe I will come to a solution to this offline, and I will post it on the canvas. Okay. So anyway, because d is a constant, let me clean up this a little bit. Because d is a constant, and we want this inequality to be true, to solve, we can always find the C that satisfies this inequality. Okay, and we can always find the corresponding n0. Okay, so that should be no problem. So the first step of the mathematical induction should be done, and as the conclusion, the running time for T of n should be bounded by the quadratic running time. Okay, so that's the point of the using the substitution method. Okay, so which means our guess for the upper bound is correct. Okay, and that's how we deal with the worst case running time for the quicksort algorithm. But for the best case partitioning, we can imagine the opposite case in which in the most even splits, the partitioning will produce two sub-areas that are almost equally long. Okay, the first half is n/2 to the bottom, and second half is almost the same size. Okay, so the total, the final recurrence can be approximated by this one, which is T of n equals 2 times n over T of n/2. Okay, and this reminds us of the merge sorts algorithm, and also if we use the master theorem, we have A equals 2, B equals 2, and the logarithm of base B of A is 1. So basically, we need to, the solution is n times the logarithm of n. Okay, and we have been analyzing the most extremely the most two extreme cases. So how about the average case? Okay, so given the inputs area, it is likely that sometimes the partitioning will return two evenly distributed sub-areas, but sometimes not. Okay, so the average case is actually much closer to the best case rather than the worst case. So because, for example, if you consider the partitioning that always produces a 9-to-1 proportional splits, okay? So for example, if we always split in each partitioning, we always split the input sequence into 9/10 of the original length and 1/10 of the original length, plus some linear time. So it could result in this recursion tree, right? Each time we have at the root node, we have the inputs n. On the left is 1/10 of the n. On the right, is 9/10 of the n. Okay, and if we split this one, it becomes 1%, 9%, and this one, it becomes 9% and 81%, right? Because that's the results of times up of a multiply n/10 with 1/10. Okay, so given this recurrent tree, we can notice that it is very unbalanced, right? The leftmost branches, it decreases really fast, and the right branches decreases at a slower speed. Okay, so what we can estimate using this recurrent tree is to look at how many levels are there in the tree. So if we look at just the leftmost and the rightmost, so the leftmost branch reaches the boundary, or reaches the bottom level when this quantity, which is the number in the node, n/10 to the power of I equals 1. That means the depth is the logarithm base 10 of 9. That is how deep the left branch should reach. And on the right, okay, when this quantity n/10 to the power of I times n equals 1, and the depth is the logarithm of n/10, 10/9 to the as the base in the logarithm of n. So anyway, the depth of the tree is the logarithm function of the n. Okay, and some branches end earlier, the right branches end later, and the left branches end earlier. And if we estimate the per level summation, so from this example, this level 1 sums up to n, and this level 2 also sums up to n. So we can use the same per level summation to estimate the total running time. Okay, so total running time should also follow the principle of logarithm of big O of n times logarithm of n. Okay, and having this guess again can let us to use the substitution method to come up with a strict proof of it. Okay, so the experience from drawing the recursion tree is that if we can always have a tree like this, then the depth of the tree is almost can be computed from the logarithm function of the total of the root node, or the logarithm of the total input size, and the per level cost is determined by the the root node. So it's common to see that if we do the proportional splits, I mean, it's normal to infer that if we do the proportional split for each node, then we're likely to have this n times logarithm of n running time. Okay, so this result can be even pushed towards a more extreme case. Say if we are doing a 99-to-1 proportional splits in each level, we can still have a very good, we can still have an acceptable result, because that is results in the same recursion tree but with more unbalanced branches. Okay, so it seems quite unbalanced, but Quicksort still runs in big O of n times logarithm of n. Okay, which is as if it is the best case splits. Okay, so that is the one of the advantage of Quicksort. So even if we're doing a unbalanced partitioning, but as long as we have some constraints so that it is proportional or something, then we can still achieve a pretty good results. Okay. So in fact, as long as the split is a constant proportionally, no matter how big that proportion is, we can still have a recursion tree of depth of logarithm of n, and the total running time remains the same. Okay. So, but still, we want to achieve the better, more balanced version, or more balanced partitioning. So that's why we can improve the partition procedure. Okay, by introduce some randomness into the partition. So we can introduce more randomness by randomly choose the pivot instead of always choosing the last element. Okay, so for example, we can define this randomized partition procedure, which is on which is basically to choose a random index between P and R, and then we exchange the elements with AR and the AI, and we return the final. We use the original, the results of the original partition procedure and return it. So we name it a randomized partition, and we can call this randomized partition into this randomized quicksort. Okay, so here's a typo. So because we named the quicksorts with randomized quicksort, so actually here it should be also randomized quicksort function procedure names. Okay, so with this randomization introduced, we are able to, in theory, we can able to achieve a more balanced split each time we call the partition procedure. Okay, so to recap, Quicksort has quite a lot of advantages. quite efficient average case, and it doesn't use additional storage space, unlike merge sorts. But we can consider the choice of a pivot to be something disadvantage, right? We got to if we don't know the distribution of the input sequence, say we are not sure, we don't know where the numbers, how the numbers are generated, then we need to bring more randomness in choosing the pivots for the sorts. So that is the first parts for the sorting algorithms, which is quicksort algorithms. And before we end, I can let me find some codes online, which I think is quite interesting for the implementation of quicksorts. Because currently in our pseudocode, we still need to write some partition procedure, which is not that straightforward to read. And if we look at the implementation in the actual programming language, it'll be much easier to read. So I read this before the Haskell implementation for quicksorts. It's quite a classical implementation. Quicksorts. I will share my screen. Okay. Screen share. So in the middle of the black box here, it's the implementation of quicksorts. Okay, so basically it's a quite neat implementation. So it's left, it defines the left sorted parts, which is a recursive call of quicksorts on the elements that is smaller than the pivot, okay? And the bigger sorted part to be the recursive call on the all the elements that are greater than the pivots. So this is the very idiosyncrasy of the specific programming languages. So what I mean is that quicksort is a commonly used algorithm in a lot of different programming environments. And the Python implementation of quicksorts can be something similar to the pseudocode that we use. But in Python, the defaults or the built-in sorting algorithm is team sorts. I don't know the details about it, but it seems a hybrid of quick sorts and maybe some insurgent sorts. I don't know. It'll be interesting to read into some of the details, the docs. Okay. Yeah, that's it for the lecture today. And the homework, let me see, is it due tomorrow, right? So if you have questions about substitution method, let me see if I can make some extra videos about it, because some students came in yesterday in the in the office hour, I've got a lot of questions regarding substitution method. So basically, the mathematical induction is the critical step. We want to show that the boundary holds for some smaller case, then it also holds for the upper case, for the larger case. But we also need to find some find the boundary case, which is the start of our proof. Yeah, I can do something on that and release it onto the canvas. Okay, and it's good to see you guys here. And let me know if you have questions. And I'm going to end the lecture today.